So now we go on and tell that once you understand the electronic stopping power, how can you actually use it? Well, first of all, let's start with a trivial example. If the stopping power would have no energy dependence, which we of course saw it does have an energy dependence, but if it wouldn't, we could use it in a very simple manner to calculate the energy loss in a depth interval, so just directly from the definition. The stopping power is d over dx, and then take this in a finite difference, delta E over delta x, and we would get this equation. In reality, of course, we saw that S is really not constant. It has an energy dependence for all energies. Instead of doing this trivial calculation, one should do an integral, and in principle, then if you integrate from the starting point to some distance x, you could get the energy loss over a finite energy range. And what's more interesting is in most practical cases, we know what the energy is, but we want to know how deep the ions penetrate. And now I emphasize this, that if the ion would travel fully straight, then we could calculate the penetration depth by solving this simple differential equation. So we get dx equals minus d over stopping power, and then the range, the penetration depth you would get by integrating this dx, so you would integrate this quantity. Well, if further on, if we would say that there is no nuclear stopping power, and for protons this is actually a pretty good approximation, because for protons electronic stopping dominates over nuclear for all energies. And then if you'd be at energies which are low enough that this velocity dependence, linear velocity dependence is true. Linear with velocity, of course, means square root of energy. Then one could actually do this analytically. We would get that the range of protons would be 2 over this prefactor in the stopping power times the square root of energy you would do with this simple integral. Well, now you heard that I said lots of ifs, and that's because I wanted to emphasize that basically these equations are basically almost always useless. So why should I use them? And the reason to that is that this approximation that the ion travels straight is almost never true. Because in reality, when an ion gets into a material, it also experiences nuclear collisions and changes its path. And because it changes its path, one cannot, to get the penetration depth, you cannot just integrate the stopping power. But this leads us to the interesting issue that, okay, since it doesn't travel straight, what is actually the penetration? And there are several different definitions of what the penetration is. So if you look at this figure, this is from Gary Wassi's book. So if you have an ion which enters here and then starts traveling inside the solid along this path, one can, with a little bit of talk, realize that one can define at least 4 different range concepts. One is the range along the initial direction, which is called the projected range, RP. And the projected range would then be that if you take the final position and project this the vector to the final position to the initial vector, then you get this point, and this is the projected range. Well, related concept, and often actually the one which is most useful practically, is how deep does the ion go, the depth coordinate of the final ion position. And if we have perpendicular impact, then of course Rz and Rp are equal to each other. Then the projected range and the depth of the ion is the same. But if the ion comes in at an inclined angle, then of course this is no longer true, because the projected direction and the depth are no longer the same. Well, then one can also define what's known as the chord range, which is the distance from the initial position to the final ion position here. And one can take the perpendicular range perpendicular to the initial direction, that is this distance here, and this is known as the lateral range. So this is essentially how much the beam is spreading instead of going straight. And finally, one can, in principle, if you follow exactly how the ion moves, then you can get the range along the ion movement path, which is known as the path length. And this path length is interesting that way. If there would be no nuclear collisions, then integrating the electronic stopping power would give the correct path length. But from an experimental point of view, it's after the ion has stopped, there is of course no way to know how it was exactly traveling, and there is in practice there is no way to measure the path length during the femtosecond timescale when the ion moves. So this path length can be a useful theoretical concept, but it's not possible to measure it experimentally. So in total, you see that there are four principal range concept, and then this penetration depth is a fifth concept, which is the same as the projected range if it's perpendicular impact. And just to illustrate this point that ions are not traveling straight, this is an illustration of ion paths in a molecular dynamics range calculation, which should be very realistic about this. As I emphasized, it's not possible to measure these paths experimentally, but in computer simulations it can be readily done. So what this plot shows is 100 trajectories on 10 keV silicon ions impacting on silicon at 20 degrees of normal, and the color scale is the kinetic energy of the ions. So the red is the initial energy, the dark red of 10 keV, and then the other colors along this rainbow scale go down towards the blue, which is then 0. Of course, when the ion energy goes to 0, it stops. And this, so for each of these plots, I mean, this final position of this plot is the final ion position. Then this, if you take from this final position, look towards the left to the x-axis straight. Now I couldn't draw straight, but it should be straight. This here would be the ion depth range or ion penetration depth. And then if you take the final position and project it on this initial vector, then you would get the projected range. And of course, finally, you should realize that in reality this is a three-dimensional effect, but plotting these things in 3D is pretty difficult for a PowerPoint slide, so that's why this is a projection of the actual parts on the XY plane, on a two-dimensional plane. And from this plot, of course, it's obvious that the ranges are really not straight. So now I hope you appreciate why I said that this can only be used to estimate the maximum range. That is the very unlikely case that the ion would travel without any nuclear collisions fully straight. And this two range distribution illustrate what this can be look like. So this was the schematic range distribution already shown in section 1 of the course. So here, this is the maximum range, which would be obtained by integrating the electronic stopping power, but much more likely is that the ion has stopped somewhere earlier, and this gain gives then, for instance, the mean range from this distribution. Well, this was a schematic. This is a real example that is from one of these simulations, but we know this simulation is fairly accurate. So this illustrates, for instance, for 10 keV hydrogen in silicon, that the maximum most likely range is about roughly 2000 angstroms, whereas the maximum is about 3500. So this equation would give the correct maximum range, but would overestimate the mean range by about a factor of 2. And well, basically due to this, it's actually this maximum range is not a particularly useful quantity. It's also difficult to measure, but when dealing with ion ranges, it's almost always makes most sense to present the range distribution. Sometimes the mean range, of course, can be used as a simplified quantity. And this is an illustration of how these four main range concepts, except for the lateral range, how these four main range concepts relate to each other. So, so this is for again for the 10 kV silicon ions in silicon. This is from molecular dynamic simulation where you actually do follow the ion path, so it's possible to determine even the path range. So here you see the dash curve is the path range. That of course is the longest because it includes all the wiggly motion of the ion. Then the chord range is the second furthest because the chord range includes the lateral spread. Then the projected range is again a bit longer because it's projected on the direction, and then the z coordinate range is the shortest. And of course, when you know the incoming angle theta, then the projected range and the z range are approximately related to each other as cosine of theta. So these two have a simple relation, whereas it's not possible analytically to give the chord range or the total path, even if you know the projected range. And here is, for those in Finland, here is Finnish and Swedish translations to these. I won't start reading them loud. I can only mention that if you are not Finnish, you can get a good picture of how complicated the Finnish language is by taking this phrase for the lateral range and try to read that out aloud. Okay. So much of the time the quantity which is used weight is the projected range or its average. Although also quite often for non-perpendicular irradiation, people use the mean penetration depth or the penetration range distribution and its penetration depth. And this is because if you do an experimental measurement of the depth profile, this is the quantity you would actually get. But then the key question is that, okay, you can't directly integrate the stopping, but how do you get it from the stopping? And originally, in the 1960s, Linhart, Schaff, and Schiot developed ways to estimate the mean projected range from the stopping, taking this scattering into account. But nowadays, computer simulations, the binary collision approximation simulations, are so fast that almost everybody wishing to have a range profile uses them. So I didn't even start writing out these equations. The BCA simulations are definitely more reliable and also are fast enough for most practical purposes to use. We will come back to these BCA simulations later in this section in the next video. But now there is an important additional aspect about the electronic stopping power. This is both of theoretical and practical interest. And that was, if you followed the discussion in the previous video and this video, we were assuming that the electronic stopping power for a given energy is the same no matter where the ion is in a solid and no matter which direction it's moving. And if you think a little bit about the physics of this, you may realize that this sounds like a bit of a questionable assumption. And the reason to that is that, of course, anybody with a materials physics education will know that, materials consist of atoms. Atoms have inner and outer electron shells, but the electron density in the inner shells is much, much higher than in the outer shells. This here is an illustration of an electron distribution in silicon in a 1-1-0 plane. So this is a 1-1-0 direction in silicon, this is a 1-0, and this is equi-electron density curves which are shown in the figure. And this data, by the way, this is based on experiments. We plotted it in our paper, but a different X-ray group measured this data experimentally, so this data should be actually quite very accurate. And and here you see that there is really huge differences in the electron density depending where you are. If you're in the middle of this ion would move in the middle of this 110 direction, the electron density would be much lower than if it would happen to move here almost straight through the ion cores. The nuclei are of course femtometers in size, so that's 5 orders of magnitude smaller than these electron density shells, so we don't really need to care about the nuclei. The probability of hitting a nucleus is very low. So considering there are huge differences in electron density, it's a reasonable assumption that the electronic stopping would actually depend on where the ion is. And very high energies and very long ranges, it's also fairly obvious that you will get an average over all directions, and that's why, for instance, this Bethe-Bloch equation for high energy stopping power works so well, because it assumes an average electron density, but if you pass a lot of ions, you will experience on average the average density. But for lower energies, this may actually be a poor or very poor assumption, and because of that, there are so-called local models for electronic stoppings, which follow the ion in a solid and then make a calculation for each collision separately, depending on how strong the collision is. Well, then there are other stopping models like the Linhart-Schaaf-Schild model and SRIM model, which are non-local. They use a homogeneous density, and then they can't describe this local variation. Well, and this difference becomes particularly important if you happen to move along one of the directions, which is a low index crystal direction, and happen to move far between the ion cores. And this kind of ions are called channeled ions, because you can imagine that they sort of move in a channel between the atomic cores. And if I want to describe its stopping power channeled ions, then it really is very important to use a local model for the electronic stopping. And now there are two types of, moreover, there are two varieties, basic varieties of local models. One are the atom-specific, like the Virchow model I mentioned. The other ones take into account always the local electronic structure of the material wherever the ion is moving, and these can be called 3D electronic structure models. Now it starts to be rather specific, so we won't go into any additional detail on this local model, but I'll just mention that in our group some 20 years ago, there were PhD students who did a couple of PhD theses on using one of these local models, and one could in the end basically reproduce the stopping power in channeling directions in all the cases where experiments were available to a fairly good, not perfect, but pretty good accuracy. So this is a couple of examples for how well the model works in a channeling direction. And there are also other groups which have obtained similar results. So the short message here is just that it's possible to describe the electronic stopping in channeling conditions quite well with these local models. However, now it's good to say that this ion channeling, it's not only an electronic stopping effect, but it's also a nuclear collision effect. And actually, much of the time, it's more important the nuclear collision effects, especially at lower energies. So for nuclear collisions, what this means is that if you look at the crystal direction, crystals, single crystals, it's fairly obvious that if you look in a certain well-defined crystal direction, the crystal looks very different than a random direction. And these two pictures, they look very different, but these are actually in a simple molecular model plotting software. This is exactly the same amount of silicon atoms in a 12 nanometer thick cube, which are just plotted in different directions. So these are really comparable. The atom size and intraatomic bonds were plotted with the exact same size in both plots. The only thing different is the rotation direction. And here you obviously see that if you look straight down the 110 crystal direction in silicon, you see basically through the crystal. If you have a more or less randomly rotated direction, it looks just like a very dense material. So it's fairly easy to understand that ion traveling in this direction could get further than if it travels in this direction perpendicular to this thing. Well, actually, it's more complicated than that, and the effect is even stronger because there is actually a focusing effect. And there is an analytical theory starting from Linhard, which describes this focusing effects with so-called continuum potentials. And this means that due to the focusing, if an ion happens to come into one of these channels, then the atoms tend to keep it focused so that it's actually difficult for the ion to leave the channel, and this strengthens further this channeling effect. So if you're interested in this theory, this is a good review article where you can read the classical theory about it and the equations. So it's important to remember that ion channeling, it's both a nuclear collision effect and an electronic stopping power effect. And then depending on ion and material and energy, one or the other may be more important for the channeling. And here is an illustration of this, but I'll show you this in animation form. So here we have 100 individual 1 kV silicon in silicon ion trajectories. This is for perpendicular impact. And this is in the so-called non-channeling direction, where we have an incoming angle is 7 degrees off normal and still rotated, twisted also 27 degrees around the surface normal after rotating it 7 degrees. So now we'll start these animations, and now we'll see what's going on. So in the channeling direction, you see that many ions travel straight quite deep. In the non-channeling direction, a few of them do get channeled, like this one here did actually get channeled, but you can clearly see that much more of the ions go into the so-called random direction and go much less deep, whereas here you see in the channeling condition lots of ions which go pretty deep. And this can be examined systematically. And one way of doing this systematically is to go through all crystal directions and plot the mean range or the nuclear energy deposition as a function of the incoming ion direction. So what's shown here is a so-called channeling map which shows mean ranges as a function of the polar angle and azimuthal angle. So this is a polar plot, and polar angle is the same as theta in this plot here. So this is the off normal, and then this azimuthal angle phi. This is then the twist angle in the plane here. And by scanning through all theta and phi angles, considering the crystal symmetry, one can then get a description of how strong the channeling is in different directions. So if you first look at this case on the right, this is plotting the mean range for 150 kV tungsten on tungsten. You see that in tungsten, the 111 crystal direction is a very strong channeling direction. There is also channeling in the 101 directions over 1, which is crystallographically equivalent, and the 001 directions as well, and then weaker channeling also in the 131 and 311 directions here. This is quite typical of BCC structured crystals. Then this is a different plot. This is 1.7 MeV gold on a foil of gold, where instead of plotting the range, in this case, practically all the ions go just through the foil. Instead of plotting the range, you plot the energy deposition in the foil, and then you get see that there is actually a huge lot of channeling directions. And in this case, in an FCC crystal like gold, the 101 direction is the strongest channeling direction. The 112 is also a quite strong channeling direction. The 111 and 001 are then weaker but still clearly channeling directions. And this is quite typical for FCC crystals. And what you see, these stripes here in both of these plots, this is so-called planar channeling. It's also possible to have channeling between planes of atoms when the energy is high enough, and these dashes here or stripes here show really these planar channeling directions. And if you're interested in details of what's described here, you can read this reference here. And from this kind of simulations, one can also analyze which fraction of ions are channeling, and the conclusion is that this is plotting in a few different cases the range distributions for amorphous material and polycrystalline material. In an amorphous material, there can be no channeling because an amorphous material has no crystal order by definition. But in polycrystalline, you can have. So here you see that, for instance, ion ranges in polycrystalline tungsten are clearly longer than ion ranges in amorphous tungsten. And the same is here for gold, amorphous and polycrystalline gold. And this is because if you have a polycrystalline material with some probability, you will hit an channeling direction. This leads to these channeling tails. And this is another way of looking at it, putting the distribution of mean ranges. This is for silicon, 10 kV xenon, silicon, and hydrogen in silicon. You see that for hydrogen, there is almost only weak channeling. This is plotting the mean range compared to the mean range in an amorphous material. So if this is 1, there would be no channeling. So you see for 10 kV hydrogen in silicon, there's practically no channeling. But for silicon and xenon in silicon, there is not only channeling, which means this tail here, so a lot of the directions are channeled. For xenon in silicon, there is also what's known as blocking. That is, in some crystal directions, the mean range is weaker than it is in the amorphous material of the same density, lower. And this is because the non-channeling directions are actually quite good at blocking the ion penetration. And actually, this concludes this part of the lecture notes. And the next video, there will be about binary collision approximation code to really simulate the ranges.